Okay, everyone. So welcome back to the CSP seminar this week. So this week it's our great honor to have Dr. Hossein Mobahi from Google Research to give us a talk. Hossein is a senior research scientist at Google, and his research is at an intersection between machine learning, computer vision, and optimization. So, and he before joining Google, he's a postdoc at MIT with Bill Freeman. And before that, he's did his PhD at the UIUC with Professor Ima. And in this talk, he will talk something very interesting about the replay between optimization and generalization in deep neural networks. So let's welcome Hossein.
Thank you very much, Jing, for the introduction, and thanks everyone for coming here. I probably don't need to use this chair, so move it out of the way. So, yeah, so for people on Zoom, if you have question, it's okay, at least with me, if you interrupt, because I may miss the question in the messages. Okay, so I'll be talking about some mysteries around generalization in deep neural networks, especially from sharpness regularization angle, and we will see how the Hessian structure can explain some of that. This is joint work with my fantastic collaborators, Jan Dapin and Atish Agarwala. Okay, so you did page down, right? We're going to the next page. Okay, now it works. I think, yeah, there was a click somewhere. Okay. So yeah, let's start from simple. So what is generalization? So suppose we are given some training data points shown as red. And this is, let's say, a supervised setting. So each of these points is representing input-output relationship. Let's say that the horizontal axis is the input, vertical axis is the output. From these points, we would like to estimate the underlying concept. In this case, it's a curve that passes through these points or close by these points, and then use that to make predictions about unseen points. For example, this cyan point, then say we measure something whose X value is this, and now we want to predict what should be the Y value. Then depending on which curve we eventually fit to this data, we can have different predictions. So why do we have different curves here? Because typically the space of models that we have are very rich. For example, neural networks, they are often over-parameterized. There are many ways that they can fit your data. And as a result of that, like with this analogy, there are multiple curves that can pass through your data. So the question is, okay, which one really generalizes? One answer to this comes from Occam's razor principle, which says always pick the simplest explanation that fits the data. Okay, very good. So generalization problem solved. We always need to find the simplest one. Not really, because the definition of simple is not well defined, right? It's like something qualitative. But if we really want an algorithm out of it, we need to formalize what is the meaning of simplicity or the opposite of that, complexity. So the course of evolution of machine learning, various measures of complexity have been introduced, as simple as counting the number of parameters, because the more parameters you have, the richer the model is, so it can fit more data. Or classic results like VC dimension or margin, if you have heard about SVM, especially normal parameters, so on and so forth. So the list can go on and on. But one of them, which I would like to talk about today, is the geometry of the loss. That also can characterize the complexity of the solution that you have found. What do we mean by that? So like in the vanilla form, if you want to solve, again, a supervised learning problem, you often have a loss function that you try to minimize. This loss function is a function of parameters. So it searches the loss landscape for a point in the parameter space that gives you a low loss value, right? But it doesn't care about the shape of the loss surface. The only thing you're asking the optimizer is to give me a point that has low loss. But if you want the geometric aspects to play a role here, you can throw additional constraints. For example, you can say, I want a minimum that is flat, because flat minima tend to generalize better. Okay, because the talk will be a lot about the flat minima and its regularization, let me first give you some intuition about why flat minima tend to generalize better. This is a cartoon. This is not real, but I think it's a good intuition. Actually, I took this image exactly from this paper by Keskar. So suppose the x-axis here is your parameter. Say you have only one learnable parameter. So that's the x-axis. And the y-axis is your loss. So you have some training data, and you can basically assess for each choice of parameter, you get a corresponding model, then what is the loss value for that, right? So you obtain this yellow curve. And suppose you have two minima on this curve. There's a sharp one and there is a flat, right? Okay. Why we try to minimize the training loss? Because we want to have a good prediction. A good prediction means that on average, we want to do well on any unseen points. In other words, we want to do well on the true distribution of the data, which unfortunately we don't have access to, right? So there is an underlying process, underlying distribution that generated our training points, right? So we don't have knowledge of that, but ideally we would like to, let's say if we had access to that distribution, we could compute the expected loss instead of averaging loss at our training points, right? And then minimize that. So that ideal loss, there's a question, yes?
Yeah, so this looks like generalization under like domain shift. Is that just like, does this flatness also apply to other generalizations?
It does, but this is just a cartoon, which uses the shift in distribution as a way to, I think, easy way to communicate. At least one reason why flat minima generalize, because it's so easy to see from this simple shift. Exactly. I was going to say that actually, these two distributions are just shifted version of each other in this toy example, right? So they cannot be the same because we know that the training is using finite data. So there is some approximation due to finiteness of our training set. But at the same time, they cannot be also totally different because our training data is sampled from the same distribution, right? So it cannot be totally irrelevant. So they have to resemble some similarity. And as you pointed out, for this toy illustration, this similarity is shown as a shift. So suppose the difference between the true distribution and the training loss is just by a little bit shift, okay? So based on this now, it's easy to understand why flat minima can do a better job in generalization. Because if I find this point during my, by the way, I think, red is test and yellow. Okay, so for training, I'm looking at this yellow point. So if I find this yellow point, okay, it minimizes my loss, fine. But look, when I look at the test performance, it's actually producing a very huge test loss value, right? Simply because at this point, fluctuation can be very high, and my test can be very different from the train. But at the flat minimum, this is more controlled. So a little bit shift doesn't really change the value of the test loss that much. So again, this is just a cartoon, not, as you said, the full picture, but I think it's a good intuition. All right, so based on this intuition, there have been many ideas proposed in the literature in order to find flat minima. So some of them goes back to 97, the paper by Schmidhuber. There are ideas that suggest, okay, let's penalize the gradient norm. And I'll tell you in a second why. Regularize the Hessian because Hessian somehow captures the curvature. So by regularizing that, we hope to find flatter minima. And eventually Sharpness-Aware Minimization, SAM, which is the latest one. And with the also major practical difference that almost all of these, except for SAM, doesn't work, none of these work in practice as much as well as SAM. So I think that's why they were mentioned sometime in the literature and kind of forgotten as well. But SAM keeps, pushing the state of the art. So in this talk, we would like to understand what is the difference what is SAM doing that those don't? Although all of them at the end of the day have one goal of finding flat minima, and some of them actually have very close relationship with SAM, but still fail to produce good results. Okay, so let me go a little bit deeper into this gradient norm penalty. I think this part of the whiteboard can be seen. All right, so this is the simplest way that you can kind of encourage your optimizer to find flat minima. So let's say you have a loss function of parameters W. So I add a regularization, which is penalizing, let's say, the gradient of the loss. And this is squared. So, okay, it basically, okay, prefers to put the trajectory in directions that are flatted, right? So that's very intuitive. But when you want to, for example, use something like gradient descent to solve this or minimize this, you need to compute the derivative of this, right? So the derivative of the first part happens to be just the gradient itself. For the second part, you get the gradient times the Hessian. So here will be the Hessian, or in this notation, it's just the nabla squared of L. So that's what I for short denote by H times the gradient. So this is what, when you want to do the update rule, you need to do. So your parameter will be updated by step size time this, right? Okay. So there is Hessian involved. So it looks like we need to deal with Hessian. And indeed, in all of these techniques, there is a connection with Hessian. Even when we talk about weight noise, we will see that this weight noise idea effectively looks like penalizing the Hessian. Okay. SAM is the only algorithm here that looks for flat minimum, but doesn't explicitly use the Hessian. And okay, why that should make a difference, that's the subject of the talk. Why, if you use Hessian, it fails. Okay.
Can I ask though, before you do that, I mean, the gradient is 0 at a local minimizer, right? So the cartoon, we still have the same minimizer, it's that cost function, right?
Yeah, so this is completely ineffective if you are exactly at the minimum.
Okay.
This is only affecting the trajectory. So
okay.
I think in the cartoon, okay, the cartoon you cannot say because you need more dimensions, but the idea is that when you start from an initialization, you have directions with different slopes, right? The hope is that when you choose directions that are with the slower slope, and assuming that you eventually can get to low loss value, which is the case with deep learning, we can always get near zero loss. This will end up with a, but yeah, exactly at the minimum, this doesn't do anything. All right. Yeah, so as I was saying, part of the issue has to do with the fact that these are second order methods and they have to use Hessian, except for SAM. We'll get to that. Okay, so what is the problem with Hessian? Well, on the surface, the most visible problem is that it's a giant object, especially if you have billions of parameters. Because if you have n number of parameters, then the Hessian is n squared. So when the number of parameters is large, this is going to be huge. And it makes problem for memory, for computation, and all that. So there is some remedy around that. Sometimes we don't really want the Hessian itself, but some function of the Hessian, for example, trace of the Hessian in our algorithm. That's like the regularizer or whatever. In that case, we can get a stochastic approximation by sampling. So that part is like to some extent taken care of. But there is a more conceptual issue when we get to using the Hessian, and that is the way that the field has been approximating the Hessian, which I'll show in the next slide. There's an approximation, very efficient approximation of the Hessian called Gauss-Newton, and this is where the issues arise, and I'll talk about that in the next slide. But basically, the main claim of the talk is that you cannot ignore the approximation error from this Gauss-Newton method. So the residual is important and plays a critical role in the fate of the algorithm. Okay, what is Gauss-Newton? Yeah. All right, so let's set up a notation. So let's say we have a model F that has parameters W and the input X. So F is the prediction, okay? And also a loss function that takes the F and also a ground truth label produces an error. Okay, gradient is easy to compute, right? You use chain rule. You can write the gradient in this form. So the gradient of the loss with respect to weights is equal to gradient of the loss with respect to predictions times gradient of the predictions with respect to weights, right? Simple chain rule. If we want second order derivative, which is the Hessian, we need to take another derivative of that. And because we have a product of two objects, we don't have the product rule for differentiation. So we end up with the sum, which first computes the derivative of this multiplied by that, plus derivative of this multiplied by this. So if you do that, in this case of like a vector matrix form, this is what you get. This part is what is called Gauss-Newton. And in a lot of the machine learning literature, the Hessian is approximated by just this term. And then there are reasons for this, which I'll explain in this slide. This part is something that, to the best of my knowledge, doesn't have a name. So we just call it Nonlinear Modeling Error, or for short, NME. Okay. All right. So why NME has been traditionally been neglected? Okay. The first is that this NME term completely vanishes at interpolation. Not any minimum, but a minimum that can perfectly predict, gives perfect prediction, exactly your ground truth label. At that point, this term vanishes. Okay, why? Let's again create a toy example with squared loss. So my model here is f of w, and I have this y as the ground truth label, and I square this, so this is my loss. All right. Now, let's take the gradient of this loss. So it becomes fw minus phi times the gradient of f, right? And a factor of 2. Okay, so if I am at an interpolation solution, meaning that all the by the way, this is also for one sample, xi and yi, and I'm summing. Sorry, I always like to use this in whiteboard because I cannot do it on anywhere else. You first write and then mess up. So this is xi and yi. Okay, so when we are at interpolation, that means that the prediction exactly match the ground truth label. So this term is 0. So regardless of what this is saying, this whole thing is 0. And this is exactly what we have here. The gradient of the loss with respect to predictions is this first term. So it's 0. So this is one of the biggest reasons that people have started to drop that term, because like at this interpolation, it just disappears. There are other reasons. For example, it's more computationally expensive. Also, it's not generally convex with respect to parameters. This one is convex if your loss is convex. So like for squared loss and cross entropy, this is going to be convex. So if you're doing theory, just skipping the Gauss-Newton part is like very good assumption, because then everything is convex and you can do a lot more things. And if you're in the if you're a practitioner, okay, this is again going to be more expensive to compute. So you tend to find an excuse to drop it. So yeah, because of these reasons, people tend to drop this term. And I give you some examples. For example, there are already some second order optimizers, like the ones you see here in the reference, which involve Hessian. But instead of using the actual Hessian, they just use the Gauss-Newton approximation. And also, there are some theoretical works that study second order techniques, and they also drop the Hessian. I think that's mainly because of the convexity. But that's one thing that is happening in the field. Like it's very common practice to drop this term. And what we claim in this talk is that you cannot simply neglect this term. It can be very significant to the point that it's actually the key to explain why Sam is succeeding while the others were failing. Although all of them are like algorithms seeking flat minima, but there's only this difference that making this huge like failure versus success. Okay. Okay, you may wonder, okay, what is this NME term is really encoding? Why is it important? Okay, there are a couple of things you can say, but the most important one is the following. It's the only part of this Hessian decomposition that knows about second order information about the model, right? So, okay, you see here, there's a second order in Gauss-Newton, but that's the derivative of the loss with respect to predictions, not the derivative of the prediction with respect to parameters. So this is the derivative of model with respect to parameters. And second order only shows up in this term. In fact, everything with respect to model is linear here, right? We only use first order. So that's the biggest difference. All right, so how is it going to affect us? All right. So let's use this example to explain that idea. So here we are having a ReLU network. We are looking at two parameters from this ReLU network that are on the same layer, because then the loss will be piecewise linear. Sorry, not the loss. The prediction, the network prediction will be piecewise linear, right? If anybody has doubt about that, I can explain here. No? Okay. Okay, so ReLU network, two weights from the same layer and L2 loss. So now this surface should be piecewise quadratic because we use the L2 loss over these linear pieces, right? So this is our loss. And here we are visualizing the magnitude, like the norm of this NME matrix as we look at different points in the parameter space, okay? So something interesting is happening. It's responding to the boundaries between these pieces, right? So I don't know if it's easy to map the 3D to 2D, but these are exactly the boundaries that are connecting these piecewise linear regions. So why this could be useful? Well, potentially this can tell us or tell the optimizer what's happening in like the adjacent region, right? So this is a signal that is leaking from this region a little bit to this region. So if gradient descent while operating in this region can pick it up, it can tell, okay, what's coming in this direction. And if you can bleeding a little bit from this direction, can pick it up, can tell what's going on. And therefore, it can have a vision about what's happening beyond these like immediate region. So inside the region, it's not that interesting. I have just a linear response function, but as soon as I get to a boundary point and I switch to another region, then the slope and everything changes completely, right? And gradient descent cannot know that without this information. This is something that is, again, leaking a little bit of information about one side to the other side. But despite this, it looks to be barely accessible to gradient descent because it's mainly zero. Although there is a signal across this boundary, but the band around it is too narrow. So it's almost zero in the interior. So if you're running gradient descent, it just follows the direction that the gradient says until it hits the wall. And at that point, maybe one step before hitting the wall, it sees this, and then, I don't know, maybe decides to change the direction, but it's already too late because gradient descent only goes in one way. So you don't want this to happen too late, right, in the training. And yeah, there is a way that we can fix that, but for now, I think the piece that I want to emphasize, we'll get to how to like make it more accessible. For now, the piece that I would like to emphasize is the importance of this NME because it allows you to explore between the regions, okay? Not just exploit the current region. The GN term, the Gauss-Newton term, only sees information about this immediate region that you're at. Okay. All right. So why NME has this structure, or why loss has this structure? Why do you have a lot of zeros here? Okay. If you understand that, then maybe we can come up with a fix. Okay. Again, to recap here, we emphasize that NME is capturing important information, but it's barely accessible. Okay. So why there are a lot of zeros? It's not too hard to see that. Again, all you need to do is to work out the NME term and see that, okay, because it involves second order derivative of the model with respect to parameters, applying chain rule, at some point, you will need to see second order derivative of the activation functions, right? Because there's a nested composition, activation weights, and then compute the second derivative, check it on paper. It ends up involving the second derivative of the activation functions, okay? So with that in mind, let's see what happens with ReLU. Okay, I think before you even see these plots, you can see what's happening with ReLU. So for ReLU, the first derivative is going to be a step function. The second derivative, which is the derivative of a step function, is a delta function, which is zero everywhere except at the origin. Okay, so this is now explaining why in that NME plot, which involved the second order derivative of the model, you saw zero everywhere except a very narrow band at the intersection of the regions.
Smooth the road a little bit. So
that's where we are going to. Okay, so, but yeah, this is getting interesting because now we are in the realm of activation functions. So let's do a little bit history and see, okay, why then ReLU talks basically for second order derivative, why people didn't think about it. Well, it's just, I think, the history. So back in the day before deep learning revolution, the dominant activation function in the literature was tanh, right? And I guess the reason for that is that it has some biological plausibility. And back then, people wanted to really imitate the brain, I think, and actual neurons can be approximated by on and off switches. So tanh or sigmoid, that's how it came into the field, I think. But then Hinton and his team realized that it was until you get to very deep network, because this was working fine for shallow network. But when you get to deeper network, which was when this new deep learning revolution started, that they realized the issue of vanishing gradient, which amplifies with deeper networks. And they realized, okay, now we need to find another solution. This activation doesn't work. So vanishing gradient essentially means that if you take the derivative of your loss, at some point, the derivative of the activation function shows up, and the derivative of sigmoid or tanh will be like this, something like a delta function. So again, it's zero in, or close to zero in most of the space, except this narrow band around the origin, right? And this is going to make like your computations very unstable because, or maybe unstable is not the right word, but in terms of the precision, we run into errors because you are multiplying small numbers because of depth. You keep multiplying, and at some point, this becomes so small, because again, this value is super small, that it goes beyond the machine precision, and you get inaccurate results, and you cannot train, right? So based on this, they proposed ReLU. This is not exactly ReLU. There is a small dip here, and there is something. But I had to do this so that I could visualize. Because, again, the second derivative of ReLU is a delta function, and you cannot see it. So this is a smooth approximation to ReLU. Actually, an activation function called GeLU. Okay, so they propose this. Pretend that this is ReLU. It doesn't have this dip. They propose this, and now this resolved the issue with gradient propagation, right? So you have good signal here, +1, and here should be -1. But the point is that you have, actually, no, 0, sorry. You have 1 in one side. So there is signal, at least on one half of the space, right? Good signal on one half of the space. So it doesn't suffer from the same issue. So for them, this worked because the main driving force was gradient descent. And you just use vanilla loss like cross entropy plus gradient descent, this should be fine. But it's only when we are dealing with second order updates, like when we are penalizing the norm of the gradient for finding flat minima, that we now need to care about the second order derivative of the activation. And now you see that the second order derivative of ReLU has the same issue as first order derivative and tan. So we are just back where we were. Okay. So I think, yeah, with this motivation now, I think maybe we can start thinking about new activation functions instead of ReLU. Maybe it's something else, but it not only has good signal for gradient, but also for its second order derivative. Okay. So one way that you can basically enhance this like a delta function shape. You can make it more like a wider Gaussian is by smoothing your ReLU. Okay, so the smoother it gets, the wider this Gaussian becomes. So there is an activation function called GLU, and then a parameterized version of that, the parameter beta, which allows you to decide between how close you want to be to perfect ReLU, and the other side gives you completely linear. So you can kind of smoothly traverse between the two. So this is what happens with the ReLU, and this is what happens with like a smooth ReLU. So now you see that all those signals that I was talking about can be seen while you are early in this region. And not only that, but because they all come, so you see the average effect. So if I'm here, I can know what's like happening on average in either direction, and therefore pick that up early on with my gradient descent to aim in the right direction. Okay. So the thing I want to show here is that now NME is accessible to the optimizer. Okay. And this is the magic. So now you compare the original. Okay, so this blue curve is SAM. And as I said, because it doesn't use any Hessian, and we will see that, it doesn't fail. But the penalty version actually starts to fail. So this is the test accuracy, and this is the strength parameter. Like I think I used lambda here, but it's rho there. So if you really start to provide a strong regularization, then that regularization is going to help SAM, but the same regularization actually is going to damage the performance for gradient penalty with ReLU. And now, based on these ideas, we should expect that if we replace ReLU with the smooth version of that, it should fix it. And maybe I spoil it first and show you that, but I'll go back to get into the details of SAM. So this is same experiment. We just replaced ReLU with the smooth version. So it now kind of matches the performance of SAM on ImageNet, and to some extent on CFAR, not still there, but yeah, much better than what it used to be. So what this is saying is that it was just the NME part that we were missing, right? Because NME was in the second order, but it was inaccessible. Now we made it accessible, and now it's working. Okay, so we have 20 minutes. I think we can go over these slides. All right, so now let me go back and talk a little bit about, so second part, and I need to take off the jacket, but maybe I can't. Okay, all right, I'll tolerate. Okay, so I told you there is a close relationship between SAM and gradient penalty, right? But we never actually showed exactly what is that relationship, because the surprise comes that despite this relationship, we have this drastic difference in performance. And then we were able to show the cause. But why they are so similar? Okay, so to see that, first let's start from the definition of SAM. So as I said, SAM is an algorithm that tries to find flat minima. It starts from this min-max problem. So it says, I would like to find a W that for any perturbation around that W, I still have a low loss, right? So this max means that for any, because if you have any, the max picks the larger one. But of course, you want to control this radius of this perturbation, right? So that radius is smaller than rho. Okay, but this is a difficult problem to solve because we cannot even solve the minimization problem, right? It's highly non-convex and use gradient descent. So what should we do with this nested optimization? So if rho is small, we can rely on a Taylor expansion. So if you do Taylor expansion with respect to epsilon around 0, then you get a linear objective in epsilon, right? And that one has a closed form. So you will end up like with the maximization. So we're focusing on the inner problem first. Maximization of a linear objective subject to a ball constraint. This is the ball constraint. And that has a closed form, especially if it's L2 ball, then the solution for epsilon ends up having this form. So it's going to be normalized gradient times rho. So this way we at least get rid of the inner optimization and we are left with only the optimization with respect to W. All right. Now we want to minimize this by gradient descent, right? So let's see what is the gradient of this loss with respect to W's. Okay. So if I compute the gradient, again, using the product rule, I end up getting the gradient evaluated at this point times the gradient of this argument, which is here. So gradient of W with respect to W is identity, the gradient of W is identity, gradient of gradient is Hessian. So that's what you see, of course, with some details that you need to work out, but there is a term that depends on Hessian. And then what we do in like practical SAM is that for simplicity, we just ignore this term, okay? So we basically, the update rule will be like this. So this is saying, compute the gradient of the loss evaluated at this point. So this is now a fixed point. So this gradient doesn't go through. It's gradient of the function, and this is the evaluation point. So this is what SAM is doing, and now you see that there is no Hessian. Okay, we did this in SAM paper as an approximation, but now today we understand that this approximation is actually helping because dealing with Hessian makes those difficulties that we saw. Okay, so this is SAM. Now, why is this related to gradient penalty? Okay, in order to see that relationship, we need to do another Taylor series. This time with respect to rho. Again, we are assuming rho is a small. So remember, this was the objective that Sam was trying to minimize for W, right? If rho is a small, do a first order Taylor series, you get this, right? If you follow these simple steps, you will see that your loss becomes like the original loss plus the norm of the gradient. So that is where the gradient penalty shows up. So this is the relationship between SAM and gradient penalty. So when rho is a small, these two are behaving very similar. And I think you saw that in the plot as well, that for a small rho, they were similar, but for large rho, they start to be different. Okay, so that's about their similarity. And again, we are back to this slide that we saw earlier. So for small rho, the gap is not that bad here and here. For large rho, it becomes bad. But after we fix the NME term, the gap is much smaller. All right, so switching between activation function, making this much of a difference is kind of surprising because For SGD, switching between activation function really doesn't make a big difference, right? I mean, people have been proposing all sorts of things, but still everybody uses ReLU at the end of the day, right? Because there is no big difference. And we actually tried this. For SGD, the difference between smooth ReLU and ReLU, both of them are around this. Like that on image that they get 76% with our architecture. So it's only when we get to, this second order updates that it matters this much.
Regulation of this with universal training. So universal is on the input gradient, here is on the weights.
Yeah, here is on the weights, but what is your question? Okay,
with universal training. So universal is
adversarial training is with respect perturbation with respect to input.
I see.
So that's not what Sam is doing.
Yes.
Yeah.
So I have a question. So, so as the training goes on, like with respect to this row, because row controls like the size of the ball, right? So did you does row stay fixed like over the training iterations or?
Yeah. In the version that we have, the vanilla version, row is fixed. So it even comes with a suggested default value, but the user can adjust it a little bit. But the idea of annealing row is something that we have thought about, but we haven't really explored that much. Okay. Because it makes sense. Same way that you anneal the learning rate, maybe you can anneal the row.
Yeah.
But yeah, we haven't worked that much. So it could be something that works.
Is that the adaptive SAM or? No,
let me see. The adaptive SAM, by the way, adaptive SAM is not our paper.
Okay.
But I think, if I recall correctly, no, they try to use, okay, so SAM puts a uniform ball, right? It's like each direction is the same, it's an L2 ball. In adaptive SAM, they say, okay, not every direction has equal importance. They put an ellipsoid that, puts like different weight on different directions, but I don't quite recall how they define this ellipse, like based on what. But yeah, the difference is in the shape, not in the radius. Okay, so SAM is also our algorithm, although it's not the subject of this talk, but because I'm the speaker, I can maybe, promote it and say that SAM was proposed in 2021. And, with these image classification benchmarks, every grad student tries to beat the state of the art every minute on Earth, right? So, and there are these like classic benchmarks like CFAR, ImageNet, SVHN. So interestingly, since 2021, SAM has been the top method, like state of the art, and has not been beaten by anyone. So you can check that on papers with code. If you look for the data set, like CFAR 100, you will see the techniques have been ranked, and SAM is on the top. I abused my power for presentation. All right, so let's get to the last part of the talk. That's about weight noise. Weight noise is another way that people used back in the day to regularize the model. So even dropout is a way of like introducing weight into the learning process. But here we are thinking about something simpler. So this was proposed initially by Bishop. It's an old idea. And what does it say? It says that instead of working with your actual loss, let's create an ensemble of models where each model is just a perturbed version of the current one. So let's say your current weight is W, you perturb it by some epsilon, and this epsilon is random. So you, let's say, draw it from like normal density. And ideally, you want to compute the expected loss, like if you average over all possible epsilon, then what is the shape of that loss? But in practice, we do sampling, right? So the idea here is that by adding this noise to your parameters, you somehow smooth the loss landscape, and therefore, again, a way to find flat minimum. We'll make it more concrete just here. bear with me. Okay, so, but let's see, okay, what is the connection between adding noise and flat minima? How does it encourage flat minima? Okay, in order to see that, let's expand our loss with respect to epsilon up to second order. This is what you get. And then apply the expectation. Because this term is linear in epsilon and epsilon has zero mean, so this becomes zero. So we end up with this plus this. And this also is easy to resolve. So it ends up being sigma squared times trace of h. Okay, if anyone needs a little bit help on this, why that's the case, I can explain very quickly. I think these are like small tricks that people should know, although you might know, but if you don't know, I think you should definitely know. So I'll explain it anyway. So yeah, we are interested, and I think Jeff will appreciate this because these are all linear algebra. Okay, so yeah, we have this thing, and we are trying to compute the expectation of this with respect to epsilon, right? So this is a scalar because this is basically a inner product, right? So a scalar is equal to its trace, right? Any scalar, I can write it as a trace. So this is equal to trace of this guy, right? And still I have the expectation. Okay, trace has this property that's called cyclic shifting, I believe, which allows you to like cyclically shift things. So did you just teach this? Is that what you're looking at? Yeah. Okay. Okay, so yeah, you can basically shift this, and this is completely equivalent to epsilon transpose H. And we still have the expectation. And then by linearity of trace and expectation, we can move the expectation inside. So we end up with this thing. This is the expectation. This is the Hessian. Okay. And this is just, you know, the covariance matrix. So we replace with sigma squared identity. So yeah, very small tricks, but I think very useful. All right. So yeah, second order expansion, we get that form. And now what Bishop argues from this point on is that for Hessian, we can drop again the residual, the NME term, because again, same belief that vanishes at the solution, so on. So the true Hessian has this form. This is just the decomposition I showed earlier. But if you drop the NME term, then you get this approximation. Okay, so you need to compute this trace. So basically, he's arguing that weight noise is equivalent to penalizing this term. Okay. And now, what is this term? If you imagine that your loss was L2 loss, squared loss, then it's easy to see that this is equivalent to, this is just a trace of the Hessian. So the full loss is L plus this sigma squared trace of Hessian. And for squared loss, that's going to be the gradient norm of the prediction. So for MSE, this is exactly this penalty. Okay, so that's how it's looking like SAM. With some difference here, like in SAM, we are computing the gradient with respect to weights. Here, sorry, the gradient of the loss with respect to weights, here the gradient of prediction with respect to weights. But still, there's a lot of things. If you want to fix this, you can go to cross entropy. The argument is a little bit more complicated there, but at the end, you end up with something that the trace of Hessian now involves the gradient norm penalty, the gradient of the loss with respect to weight. So this is now closer to SAM. So we just need to go to cross entropy. Okay, so is what Bishop is saying really correct? Is it true that we can drop the NME term and basically just work with that? So here, in order to see that, we are comparing a bunch of techniques. Some of them are like even from previous slides. So we have SGD, SAM, penalty SAM. We already know how to fix penalty SAM. So in all these experiments, we are already using GLU. So all these networks are already using GLU. And then for the ones that have a penalty form, this is the form of the penalty, right? So the thing you see here is that actually when you use the Gauss-Newton approximation, so that is when you drop the NME term, the performance is better than weight noise or Hessian penalty. Hessian trace still has the NME term. It's like Gauss-Newton plus NME. So it's doing better than both of these, suggesting that, again, NME is important. This time dropping it is important. It's the opposite, right? But the point is that it's something that you cannot neglect. You cannot say it doesn't matter. It matters. If it was there, it would hurt. And weight noise is not doing well. So yeah, although the idea was inspired by weight noise, I think similar story. Their idea was inspired by this. But yeah, it ended up with something that works, but it's not really because of this, but because they deleted something. That was, I would say, maybe important, but that was significant. Okay. I think this is more or less all I wanted to cover. And yeah, let's just make the conclusions. Okay, so I think this work can provide some insight into some of the issues that we have with second order updates in deep learning. And the main message was that if you're using Hessian and using this decomposition, remember, you cannot neglect the NME unless what the field has been telling you so far. You cannot do that. And we used two examples, the difference between SAM and penalty SAM, as well as the weight noise, in order to say the importance of, in order to show the importance of this NME. And finally, we discussed a little bit during the talk that now we see, okay, there was a day that people were only thinking about loss and gradient descent, and therefore second order derivative of the activation wasn't an issue. But now with SAM and other flat minima, you know, producing state of the art, maybe it's time to think about maybe another activation function. So could be you proposing something. We want something that is well behaved for both first order and second order derivatives, passes the signal. Although smooth ReLU does that, I don't know if that's the best you can do. So that's something that you can consider as future direction. And that's it. Thank you.
Thanks, Hossein, for the great talk. Any questions from the audience?
Yeah, Andrew.
Yeah, thanks for the great talk. So I was curious whether the same insight about the behavior of these nonlinear activation functions applies to other second order optimizations. Like you mentioned KFAC at the beginning of your talk. Do you think that it'd be a good direction to examine how those affect the
Yeah, I think, yeah, that's actually very important. I think this should be something that, yeah, be investigated, but mainly by people who are working on second order optimizer, like same people that propose KFAC. So that's gonna be Roger and James Martin. So, because I'm not working on second order optimizer, but I think with this result, actually I tried to ping one of the people that has worked on efficient implementation of that. But yeah, I haven't got a response. Maybe they didn't take us seriously. They haven't seen these results yet, how much it can make a difference. But yeah, using it in second order optimizer is, I think, an obvious thing to try now with this.
Thanks.
Yeah. Okay.
You go ahead.
Okay. So I was just wondering, you considered the activation functions, but not like the loss function. There are some loss functions that are very similar to ReLU, like there's an hinge loss, which doesn't perform very well for like classification in neural networks. So I'm wondering if you have any insight into that, like the impact of the loss functions on this.
Yeah, that's a good point. So yeah, the whole thing matters, right? So at the end of the day, you are doing an update rule that involves the derivative of the loss, derivative of the activation. So all of those matter. But I was going with the, because already like L2 and cross entropy are, kind of well behaved. At least we don't have this kind of issues with non-differentiability, right? At least they're differentiable. It's only with ReLU that we have this. Also, tanh and things like that, they're close to step function, which is non-different. So they, to some extent, have those problems. But the loss itself is not, to me, that much of a problem, unless you insist on using other loss. As you said, for some reason, you have to use hinge loss. And okay, then yes, you need to think about maybe an alternative, like what would be a smooth hinge loss or something, which I'm sure there exists like versions of that. But for deep learning, because the dominant losses are just cross entropy and L2, I didn't mention it. The part that's really annoying is the activation point that have these ugly kinks in non-differentiability.
So when you go from the ReLU to the GILU, there's an additional parameter to tune, right? The rounding of the corner. How much graduate student descent or whatever went into optimizing that to get the nice table of results, or is it pretty insensitive?
No, I believe it should be sensitive.
Okay. That's what I kind of thought too from your sort of contour plots that you showed.
Yeah. So it depends on, how big is your land, right? Exactly. For each of these piecewise linear regions, if you have like bigger pieces, then you need, I think, bigger diffusion. But God knows what is the size of each of these pieces. So yeah, you need the graduate descent eventually. Yes.
I have a question about generalization theory. Yeah, so like generalization with respect to VC dimension or margins, there's like mathematical statement for that. But for like generalization with respect to the sharpness, is there any, or do you foresee any like regular statement for it?
Yeah, there is. Like even the SAM paper has some pack-based bound generalization, but they are not tight. So actually, we did a little bit of cheating there. So so the perturbation is adversarial in SAM, right? So the way we did that, we did the proof for that was that we first proved the bound for like the average case. So you take the expected like sharpness rather than the worst point causing the sharpness, and then said that okay, that give us a bound on the adversarial one, but it would be cleaner if you could argue, like we feel that the adversarial one is doing better because we did some quick experiments. It's definitely faster because you don't need to evaluate multiple points. It's just one point. But also, yeah, it seems to empirically give you better generalization, but we don't have any theory why. But I'm saying it would be at least better if we could directly, use the worst case in the bound rather than using the average as an intermediate, which we know that it's not doing the right thing. So yeah, I think there is room to improve that, but there are Bayesian bounds in our paper, and also we refer to some similar results in the literature in that paper.
To follow up this question, so also, a little bit beyond this talk, so I also noticed that you have some work on the low rank. SAM promotes low rankness. So do you have any insights? Maybe the SAM is promoting low rankness is like converging to some low complexity models that the generous bound will get tighter versus like sharp minimizers, or do you have any?
So you're asking if this low rank phenomenon can be used to get a tighter generalization bound?
Right.
We haven't tried it, but there is definitely connection between, at the very least, you are reducing the I think, not exactly the count of parameters, but yeah, definitely controlling the freedom of the models, making it less expressive. So I believe it should be straightforward to use that in order to get a generalization, but we haven't explored it yet. There are just too many things you can do, and I think, yeah, this is actually a very good audience for students, because I think there are a ton of problems. So because SAM itself is a very new algorithm, right? It's just from 2 years ago. And we use a lot of approximations, and now a lot of questions have arisen, a lot of extensions. So because it's new, I think it might have a lot of low-hanging fruits. Any of these questions that you're asking could be a paper. So yeah, I encourage people who are interested in the optimization generalization to maybe take a look. Yeah, what you're saying is very sensible.
Interesting.
Okay.
Okay, cool. Any questions? Maybe from the Zoom?
Oh, Zoom.
No.
No. Okay.
Okay, so maybe let's thank the speaker again.
Okay, thank you very much. You need to stop recording.
That way,
Yeah, exactly.
once it's